Hi everyone, welcome to yet another webinar in this series of MI2, which is Machine Intelligence on Modern Infrastructure. My name is Janakiram. I'm going to be the speaker for this session, and I'm pretty excited to bring you accelerating neural networks with Intel Movidius. So this is going to be an interesting session where we take existing trained models and optimize them for inference. So if you are new to MI2, let me set the context. This is a webinar series that primarily focuses on machine intelligence, which includes IoT plus AI plus deep learning and machine learning. Modern infrastructure, which includes Kubernetes, Istio, Prometheus, and cloud-native computing technologies. The idea of this series is to bring you the cutting-edge emerging technologies and demystify them for you. So this series delivers 2 webinars every month, and the current one is all about machine intelligence, where I'm going to talk to you about a very interesting device called Intel Movidius. For further sessions and the upcoming calendar, please visit mi2.live and register for some of the sessions. So let's get started. If you have been attending some of my machine learning sessions, I talk about life cycle of a machine learning model. I'm going to do a quick recap of this, though this is not a deep dive into the life cycle. I'm going to touch upon the various stages of machine learning. After that, we talk about the need to accelerate ML models for inferencing. So while I explain what is the difference between training and inferencing, I'm going to talk to you about the requirement, the need, and the demand to accelerate ML models in runtime, particularly for inferencing. And that leads us to a discussion on Intel Movidius. And I'm going to do a deep dive on Intel Movidius Neural Compute Stick version 1. And we'll also take a look at how to use Movidius SDK for optimizing the models. So I have a pretty interesting demo towards the end. So stay tuned. Let's get started with this session. So what is the life cycle of a machine learning model? Well, machine learning, whether you do it as a classical machine learning training or you do it with deep learning, essentially has multiple phases. So one of the first step is basically to take the historical data set and split that into a test data set and a training data set. And the training data set is passed on to an algorithm that is most appropriate for the business problem. And the outcome of the combination of data set and algorithm is thoroughly tested with the evaluation and test data set. So basically, the algorithm will generate a new classification or prediction. And because this is on existing data coming from the test data set, it is constantly evaluated, and the training process goes back and forth till the delta between what is predicted and what is actual is minimum. So that is the fundamental process of machine learning. And once the model achieves a level where the prediction is very close to the actual value, the model is set to be fully trained, and it moves into the next phase where production data, which is unknown, unseen, live data, is passed on to the model, and it comes out with the prediction or an expected outcome. So that is the life cycle of a machine learning model. If you are interested in understanding each of these steps, do watch my video on Azure ML services, where I have gone through this process and the pipeline in detail. So what is the difference between training and inference? Well, a machine learning model will essentially have 2 lives. The first one is during its development, which is the training, where we take historical data, split that into a test data and training data set, pass it through an algorithm, and then constantly tune it till we are happy with the predictions or classifications. So that is the training phase. When we send production data for real-time use cases and in real-time deployments, the model lives in another phase, which is called inference. So training is more like design time, and inference is like runtime. So the data scientist, a statistician, a programmer will work in tandem during the training process, and finally the evolved model is handed over to a developer or a DevOps team to be deployed in production environment. And from there, it basically becomes accessible to rest of the consumers. So that is the high level overview of the life cycle of a machine learning model. And this is how all the training, all the machine learning models are evolved and used. It doesn't matter whether you're doing plain vanilla linear regression or you're doing one of the most advanced generative adversarial network, it doesn't matter. Everything follows exactly the same workflow. What is more important for this session is the inference part. Now, the model that is being generated can live either in the data center or in the cloud or in offline environments powered by edge devices. And these edge devices are very memory constrained and resource constrained. Think of it like a Raspberry Pi. It may be different from a Raspberry Pi, but it definitely doesn't have the horsepower to run full-blown machine learning models, or they're not really ideal for training. So they are meant for running the fully trained model for inference. So there is definitely a need to optimize these models to run in a variety of environments. And that is what is the inference optimization, or it is also called as an acceleration. So why do we need to accelerate ML model? And acceleration is not just about inferencing. Even during training, we need to have a faster training and higher throughput. So basically, both training and inferencing are highly intensive. They are very compute intensive. And there is a concept called an epoch, where basically the entire data set is being used for one iteration, and that epoch goes through complex computation, and we may have a few tens of epochs to hundreds and thousands of epochs that are used for training. And our goal is to make sure that with every epoch, the model is optimized and it is reaching a higher accuracy level. So that means with every epoch, we need to perform more and more computations and more rigorous calculations. And CPUs alone are not sufficient to perform that. So to help CPUs with the computation process, we have GPUs, the graphical processing units or graphics processing units, that are complementing CPUs to deliver additional throughput through massive parallelization. So what would take a few months with just CPUs for ML training will be reduced to a few weeks and sometimes a few days with GPUs. So that's how GPUs accelerate the training process. The number one goal of ML training is delivering higher throughput, which means training larger data sets with complex neural network architectures at a very high speed. That is what is the goal of ML training. Now, the second phase, which I mentioned as inferencing, they run in extremely constrained environments. And AI at edge is becoming the most common deployment scenarios. What I mean by this is, imagine a scenario where you have trained a machine learning model for object detection, and this model is now deployed in a real-time environment as a part of a CC camera deployment. So every time an object shows up, for example, we might train this model to identify weapons or some of the sensitive objects, and every time it shows up in the camera, an alert has to be sent out. So while the training can happen with a GPU-based cluster in the cloud, the model is going to be deployed in a very constrained environment running as a part of the CCTV, a closed circuit surveillance camera network. So there we need to basically detect an object in a split second and then perform that at a very higher speed with reduced latency. And that is the important goal of inferencing. So to summarize, the goal of training is to achieve higher throughput, while the goal of inferencing is to reduce the latency, which means when there are fast moving objects that are captured by the camera, and if there are objectionable objects or objects that you want to identify and raise an alert, you need to do that as soon as possible. And that is what is now referred as reduced latency with inferencing. So these are the two aspects, and there is a need to accelerate both the ML training and inferencing. While training is highly accelerated through GPUs, TPUs, and FPGAs. So GPUs are the graphics processing units, and TPUs are Google's proprietary accelerator available in their own cloud environment, the Tensor Processing Unit. And some of the other techniques are FPGAs, the field programmable gate arrays, and Intel, Microsoft, and some of the other vendors are using FPGAs to accelerate training. So that is happening on the training side in the public cloud. And when it comes to the edge scenarios, particularly for inferencing, we need to have additional devices that essentially accelerate the inferencing. So there are a lot of niche specialized chips, system on chips that are actually coming up to accelerate inferencing at scale, at a very reduced latency. So some of the examples of these devices or chips is NVIDIA Jetson TX2, a very popular chip that accelerates ML inferencing. There is an updated version of Jetson, which was recently launched, called NVIDIA Xavier, and this is also meant for accelerating ML models for inferencing. Intel has a chip called Myred, and Myred is very, very special. It is a very niche device meant for accelerating vision computing. That's why it is called VPU, Vision Processing Unit. It is typically attached to a camera, and when the frames from the camera are fed to this chip, it can accelerate inferencing and reduce the latency and identify objects pretty quick. The most recent announcement from Google, which was called Coral, came out with Google's own Edge TPU. So this Raspberry Pi-like device is actually Google's own edge device, and it runs its own TPU, highly optimized for the edge. And when a model that is trained in the public cloud on a GPU cluster, when it is deployed on the edge TPU, it achieves a pretty good performance with reduced latency. That is the goal of edge TPU. So these are some of the available options, but the most popular one and most affordable one is actually called as Intel Movidius Neural Compute Stick. Interestingly, this device is powered by the same Myred chip, which is called the Vision Processing Unit, but the form factor of this device is like a USB stick. So you don't need to assemble anything. You don't need to have breadboards or jumper wires or specialized IoT kits to attach these VPUs to your machine. Instead, just plug and play through the USB stick. So there are two versions of the neural compute stick. There is a most recent version, which is called NCS2, and the other version has been around for a couple of years, and that is the first version, NCS1. Intel has not deprecated or retired. It has not retired NCS1. This is still very active. It is actively maintained, actively sold, and there is a large community around it. And it is fairly easy to get started with NCS1. The focus for this session is basically NCS1 and its associated SDK. In one of my upcoming webinars, I'm going to talk to you about NCS2 and the software, the SDK and the toolkit associated with it, which is called OpenVINO Toolkit. But that's for some other topic and some other session that I'm going to schedule in the next quarter. So what exactly is Intel NCS V1? Well, it is a USB stick-like device powered by Intel Myred 2 Vision Processing Unit. It basically optimizes models trained in TensorFlow and Caffe for inference. So if you have pre-trained models of TensorFlow or Caffe, you can use the tools and the SDK to basically optimize them to run on Movidius. So you cannot, unfortunately, take an existing TensorFlow protobuf or a checkpoint file and directly run it with Intel Movidius. Similarly, you cannot run a Caffe model directly on Intel Movidius. You need to process and create an intermediate graph that is highly optimized for the device, and that is what is going to be used for inference. So that's the reason why we call out the supported frameworks. Now, in terms of connectivity, it is backward compatible with USB 2, but highly recommended to be used with USB 3 because you get better bandwidth and better throughput. It runs in two modes. One is you take a model and you optimize it, and this is typically done on an Ubuntu 16.04 box. So you need to install what is called as a Neural Compute SDK, and this SDK runs on an Ubuntu 16.04 box, and there you're actually using the tools that are responsible for converting an existing model, existing Caffe or TensorFlow model, into a graph that is understood by the Intel Movidius SDK. So that is what is done on an Ubuntu 16.04 box. But once you generate the graph, that can be easily moved to a Raspberry Pi, and you can use what is called as an API mode of the device to just load the graph and perform inferencing. So there's a workflow which I'm going to talk to you about. And then the other requirements are basically you need to have at least 1 GB of RAM for both optimizing as well as for inferencing, and abundant free space to clone the GitHub repo of NC SDK and the app zoo that I'm going to talk to you about. Spending a bit of time on NCS V2. This is the most recent one, and it basically runs on the same Myriad chip, but more advanced and more recent one. It comes with 16 processing cores, unlike the previous version, which came with 8. And this supports TensorFlow and Caffe, but it also supports additional toolkits and additional frameworks, including Onyx. Onyx is Open Neural Network Exchange. And this is not running exclusive SDK or tools meant for just the Movidius NCS, but it uses a slightly broader platform, a broader toolkit called Intel Open Vino Toolkit. So this can be used not just with Intel Movidius. The Open Vino Toolkit is available for a variety of environments, including Intel FPGA, Intel Xeon, and of course, the Movidius environment. So very recently, Intel has added support for Raspberry Pi, but that's like almost a week-old update. So I haven't updated this slide because this has been like the most recent one. But technically, you can run Intel NCS V2 with Raspberry Pi and OpenVINO Toolkit. But as I mentioned earlier, the focus of this session, this webinar, is all about NCS and NC SDK. So in terms of performance, Intel claims that NCS2 is at least 8 times better than NCS1. And you can actually see that the image classification and object detection happen much faster with NCS2 than NCS. So that is the difference. And if you are actually planning to use this in production, or you are basically considering using an accelerator for inference, you should absolutely go for NCS2. But if you are looking at a very straightforward mechanism to port your existing TensorFlow and Caffe models, and you want an affordable environment with easy to use tools, then you can still use Intel Movidius NCS. So how do we get started with NCS1? Well, as I mentioned, there are 2 different hosts for the device. The first one is a development host. You need to have an Ubuntu 16.04 desktop. It can even be a VMware Fusion or VMware Workstation running in Windows or Mac, but you can run the tools only on an Ubuntu box. And that is going to run the full-fledged Neural Compute Stick SDK and the required tools. The inference host, where you actually run the graph in real time for inferencing, that can be either the same Ubuntu 16.04 environment or even a Raspberry Pi 3. So there you're going to use the SDK in API mode. So API mode is a shortened, constrained version of NC SDK that is meant for pure inferencing. It doesn't come with all the tools and the tool chain, but it is predominantly meant for loading the graph and performing some operations on it, which is very typical to inferencing. So that can be run on a Raspberry Pi. So if you actually look at the graphic on this slide, there are three phases. The first one is you're going to train a model in the cloud, and you bring that model onto your development host, plug in your NCS stick, and run an optimization process to generate an intermediary graph. And then you load that graph on a Raspberry Pi or a supported environment and use it exclusively with API for inferencing. So those are the phases involved in using NCS1. So as I mentioned, there are three major steps. Train the model in the cloud. You could use Amazon SageMaker or Azure ML or Google Cloud ML Engine or Paperspace, any of those environments to essentially train your model. Once you train the model, you profile and generate the graph from that model, optimize it for the neural compute stick, and then load the graph for inference. This is going to be running at the edge in an offline mode with no connectivity to the host machine or to the cloud. So every time you generate a new version of the model, make sure you generate a corresponding graph that is loaded for inference in one of your target environments. So getting started with NC SDK is pretty straightforward. You can clone the repo. So more recently, I think almost 8 months ago, Intel has released the second version of NC SDK. So that's the reason why I added -b for the branch of the second version. So you clone that, then you get into the directory and simply run make install. This is going to take 15-20 minutes because it's going to pull a lot of dependencies, updates Ubuntu, and sets up the entire test bed for optimizing and generating the graphs. The other important add-on to NC SDK is called the NC App Zoo. So NC App Zoo comes with a lot of pre-trained models and pre-generated graphs that you can straight away use with your applications. So you don't need to really train the model completely or run the optimizer, but the NC App Zoo comes with a lot of pre-trained models. For example, face detection, RetinaNet, LXNet, GoogleNet, LayNet, all of those are already built and readily available. So you can basically take an existing model, and if you want, you can optionally generate the graph, or you can even use some of the existing graphs that come with NC App Zoo to directly load in your Python script and start performing the inferencing. So that is the straightforward process to install and configure NC SDK. So you can optimize Caffe models. For example, I'm going to show you a demo of optimizing a convolutional neural network trained using Caffe on a GPU, and then we are going to use that for inferencing with Movidius. So the workflow for this demo is going to be training the Caffe model through NVIDIA Digits. Then we download the model and we generate the graph that targets Intel Movidius. And then we profile, we check the graph, and finally we run the inference. So let's get started. This is going to be an interesting demo. So the first one is to basically walk you through the tool chain and what's available. So I have an Ubuntu 16.04 box here, and this has the SDK fully configured. So the NC SDK directory is where you'll find a lot of existing tools and the entire SDK. So if you actually run make install here, this is going to take a long time. I'm not going to do this because it's going to take a while to install OpenCV, the dependencies, and download a lot of stuff to basically configure it. So simply clone, move into the SDK directory and run make install. And once you have make install, you'll actually notice that there is another directory called API. This API is a subset of the NC SDK, and if you are actually installing it in your target machine, you simply need to clone this repo and enter into this directory called API and type make install, and that will only install what you actually need for performing the inferencing. It doesn't come with all the tools, and it doesn't install the entire framework for optimizing the models. It assumes you already have a model that you can directly load through the Python SDK. So that is the API mode. Now, this is the existing environment. Now, I installed this in a virtual environment within Python. So I'm going to set the virtual environment. And how do we know whether the device is recognized or not, or even connected or not? When you actually run LSUSB in your Ubuntu box, you should actually see that there is a device with ID 03E7. And as long as you can see this, you're rest assured that the device is indeed recognized by Linux. Now that is the first step. So once you made sure that the device is connected and recognized by the operating system, the next step is to make sure that the SDK recognizes this device. So for that, we move into examples apps directory, and within that there is something called hello NCS Py. So we move into that directory and simply run make run command, and this is going to kick off a Python script that basically gets the entire metadata about the device, and then it actually shows that the device opened normally, hello NCS, and then it gracefully closes the connection to the device, and it prints out NCS device working to STD out. And this is a great indicator that the SDK is installed perfectly well and the device is indeed connected to the machine. Once we have this, we can move into other applications. For example, within Caffe, I want to show you a simple LXNet application. So here, when I actually do a make run, this is going to perform multiple steps, and then basically from this code, it is going to execute the inference. So it takes an image and it prints out what it actually sees. So it actually printed out electric guitar because that is what is being used. We can actually take a look at run.py, and you'll actually notice that we are passing the image called electric guitar.png. Now I can safely change this with let's say baseball.png. So let's see if the model still works. So I changed the image. By the way, these images are available here. If you go to examples data, and within that there is images directory, and you will see a lot of test images, sample images that you can use. So now when we go back to Caffe, LXNet, and do a make run, since we changed it to baseball, this time the inference actually shows us that the image that is passed on is indeed a baseball. So it actually says baseball with 100% probability. This is how we perform inferencing, and both these are actually tests for us to perform in terms of the installation and verifying that the SDK is installed the right way. All right, so now we have the device connected to the machine, and now we have SDK verified. It's time for us to do something more meaningful, and for this I want to switch to one of my previous discussions on what is called as NVIDIA Digits. So with NVIDIA Digits, we actually have a very nice GUI like environment to perform convolutional neural network training. And if you have attended my previous session on NVIDIA Digits, you're already familiar with this because I have actually gone through the full details and walkthrough of using NVIDIA Digits to train convolutional neural networks. So we have a data set that is highly customized with a sample of cat images and dog images, and then we have gone ahead and trained this with with the LXNet and Caffe architecture. So this model is fully trained. In fact, this was trained back in July when I was actually learning this, and the model is now completely trained. And if you look at the graphs, this model claims to achieve 84% accuracy, which is pretty good. While we are at it, we can also test by feeding some sample images. So, here I have, let me show you the images I have, and then we can. So we are going to take some sample images. This is like one of the dog images that is already pre-processed. I think I have resized it to 227 by 227. So I have some images and I want to pass them to our fully trained model just to make sure that the accuracy is good enough for us to move it over to inference. There we go. So now the trained model predicts that the image is dog with 78% accuracy, not bad at all. Let's pass 4.jpg. I deliberately named it with numbers and not the actual name like cat.jpg, just to keep it neutral. So when we actually pass this, it should predict a cat, because 4.jpg is a cat with 93.4% accuracy. Fantastic. So now this is a fully trained model available for our disposal. Now it doesn't matter whether you train the model or you get the model from an existing environment, or someone else would have trained and made it available. So it doesn't matter. All you need is either a TensorFlow protobuf or a checkpoint file, or a Caffe file with a Caffe model and deploy.txt that actually contains the trained model neural network parameters. So assuming I go ahead and download this model. So when I click on download this download model, it's going to give us a zip file with multiple files. But what is very important and what is required for us is actually the .caffe model and another file called deploy.proto.txt. So we'll take those two files and then we'll optimize it for Intel Movidius. So when I downloaded the model, I would have actually got multiple files, but I have already separated these two files. So one is deploy.proto.txt, the other one is cat.caffe model. So we have these two. Now the goal is to actually run this Caffe model with Intel Movidius. So there are multiple steps involved. Let's go through them. The very first step is to take this model and generate the graph. So I have this step called compile, and I'm going to get rid of the files that we already have. So we have an empty directory here, and our goal is to take the existing Caffe model and generate a graph, compile it into a graph that is understood and read by Intel Movidius neural compute stick. So we are going to run one command, and this is how it's going to look like. mvncc compile. By the way, mvncc compile is a tool that you get. It's a CLI. Technically, behind the scenes, it's a Python script. And what this does is it takes an existing Caffe model along with proto.txt file, and it actually takes how many shave cores. So just like a CPU has cores, the Intel Movidius stick has what is called as a shave. Think of shave as a micro core. So I'm passing in 12, but this can be anything. Maybe I use 12 because I've been playing with the models that actually deliver better performance, but it can be any arbitrary number within the range of the NCS supported number of shapes. I think the optimal value could be 8 because technically speaking, Intel Movidius NCS1 comes with only 8 cores, 8 shapes. So this could be 8, but I don't want to tamper with this. It's 12. Let's leave it with that. And then the input image size, which is IS 227 by 227. That is the image size that we are going to pass for inference. We also need to mention that when we are actually passing on the image. So we'll simply pass these parameters and hit enter, and this is going to generate a couple of files. So it actually tells blob generated, and now when we do an ls, we notice there are 2 files. One is graph, the other one is output expected.npy, and this is a numpy file, a binary file that actually contains some serialized numbers that are going to be used during inferencing. Maybe that contains the actual weights and biases and the hyperparameters required for inference, but this is not a readable file. It is used by the NC SDK when you actually perform the inference. Perfect. So now we have the graph. And once we have the graph, we can go ahead and run our actual inference. So now I move into the infer folder, and here I basically create a file called labels.txt that contains the classes, for example, cat and dog on separate lines. So we put that, and then I have some sample images that I have already shown you, a couple of images of cat and dogs, and then we have the actual run.py, and let me actually show this to you in Sublime, which will make it more readable. So under infer, we have run.py. So this is where the actual magic takes place. So we import mvnc.mvnc API. That is the most critical part. And even if you're running this just on a Raspberry Pi with a live camera, you can still use it because we are only using the API mode. And then the graph, NCS compile graph, this is the path. So this is what we generated in the previous step. So let me get out of this, right? So that is the graph. So if you actually look at compile, there are 2 files that we generated in the previous step. So we load that graph, and then we use the size, which is 227 by 227. That is the image size, the dimensions. And then there is some basic hygiene, where we check for the devices before we go ahead. And once the device is found, we open the first device. By the way, you can connect multiple devices and parallelize the inference across all the devices. So in our case, we only have 1. So we are basically using the first device. And while opening the graph, we are performing the functions that are actually required by the inference. So this is how we move the graph to the device. This is where the offloading from CPU to Movidius happens. After that, we take the image and we make sure that it is resized to the exact dimensions that are mentioned, and it also loads the labels.txt file to print out meaningful labels. Otherwise, you'll actually see some arbitrary numbers that doesn't make much sense. So we basically have labels.txt to map out the output with the appropriate line numbers available in the labels.txt. And after that, we execute or we invoke graph.q inference with FIFO element and some parameters go into it. You can actually read the documentation and the SDK for the parameters and all the details for each of these methods. But finally, to actually get the prediction, we use output.orgmax, and then we map it to the labels file and print out what is the top prediction. So Once this is done, we basically close the FIFO stream, and then we close the device and we release all the resources. So this is almost like a boilerplate code for loading any graph and running it with Intel Movidius. So this is pretty straightforward. So let's go ahead and run this application for inferencing. So now what I'm going to do is, when I actually run run.py with, for example, image2.jpg, so this is going to perform the inference, and when we are there, we go. So image2 is a dog, and it took roughly 90 milliseconds with 96.6% confidence. One overhead, for example, when I run images3.jpg, you'll notice that there is a bit of latency. And if you're wondering what acceleration is being done, well, this is a demo, and in this demo, what we are actually doing is we are opening up the device, we are loading the graph, we are performing some housekeeping, and then we are releasing and destroying all the resources. In real-time environment for inferencing, we don't do it per image. We don't do it for each frame. Instead, we open the device, we load the graph, and we pass every image or every frame at runtime while the device is still open. And that is going to be extremely fast than what you're seeing here. This is a CLI that is doing one image at a time by going through the full cycle of opening the device, offloading the graph to it, then running the inference, and then closing all the resources. That is not the case in real-time inferencing. It's going to be much faster. All right, so now I'm going to run the last image, and that's again a cat, and we'll notice that Movidius is saying it is like a cat with almost 99.4% confidence. Fantastic. So this is how you basically go through the steps involved in taking an existing Caffe model trained in the cloud. In this example, I actually trained it with my existing machine. So this is a GPU based machine. I've done it locally, but it doesn't matter. You can run your training anywhere. And we took the training model, trained model, we ran it through the Intel Movidius SDK, compiled a graph, we loaded the graph and performed inference. Now I want to show you something much cooler, much realistic. Unfortunately, I don't have time to go through the entire process, but it's not very different from what I have shown you. So for this, I'm going to switch on my camera. Let's see how far it's going to work. So what I'm going to do here is to turn on my webcam, and let's see if this really works. Okay, give me a second. I'm just turning on my webcam. All right, there you go. So I hope you're able to see my webcam, the output from my webcam. So what you see here is actually a ruggedized Raspberry Pi. So this Raspberry Pi is connected to a camera. And what I like about this setup is it's like Lego blocks. The camera is just snapped to Raspberry Pi case, the cabinet, and this is the cable. And this is amazing for inferencing. I can basically move it around, and it can run anything that I want. So you actually see this. Now let me turn off my webcam and take you back to the code window. So what I'm going to do now is SSH into my Raspberry Pi. Okay, so now we are inside Raspberry Pi. I go into this directory called workspace, and we have NC SDK here, but that's being installed only in API mode. So we don't need to install the entire toolkit. But there is also something called NC App Zoo, and this is again available on GitHub. I just cloned it, and within that there are multiple apps, and when you actually look at apps, you notice that there is an image classifier, there is a live image classifier, live object detector. A lot of pre-trained models and optimized graphs are already available, so you can actually make use of them. So in our case, I'm actually going to run a live image classifier, and this, or I think my demo is about live object detector. Yeah, so I'm going to show you a live demo of how the images, or rather the objects, are being detected. So I'll actually run Python 3 live object detector followed by rpy.py. Okay, so now this is actually going to kick off. Okay, that's a good message, you know. So I haven't pulled out the Movidius stick from my development host, so which I'm actually doing it now. So I pulled out the NCS stick from the development machine. I'm plugging this into my Raspberry Pi, and again, let me turn on the webcam and show you how this setup would actually look like. So now you'd actually notice that, you know, there is an NCS stick attached to my Raspberry Pi. It looks pretty cool. I really like this ruggedized look and feel of Raspberry Pi. And I'm going to use one of my favorite demos. You know, I have a tiny toy car, and this tiny toy car will be detected by our camera, and it's going to print out the actual devices it sees. You know, while during this webinar, it may be difficult for me to show you both the windows. What I'm going to do is, now that you are familiar with this setup, I'm going to turn off the webcam and just show you the output, the objects that are being detected, right? I also have a tiny model actually detects this in real time. Perfect. So I'm going to leave them here, and to save bandwidth and to make sure that you actually see the output and not my face, I'm going to turn off the webcam. All right. So with the device connected, I'm going to simply run the Python script, and now this actually shows me, you know, so when I point the webcam towards me, it says it is actually seeing a person. And I'm now going to point this camera at there we go. So now, you know, I'm pointing this to the toy car, and it actually says it's able to see a car. And I'm going to remove that from the frame, and it actually picks up my computer desk, and it says it's able to see a dining table. Not bad. So I'm now going to place the bus, and I'll point this, and hopefully there we go. So now in just a split second, it detected bus. So it's also picking up my laptop screen and says it is actually a TV monitor. That's not a bad thing, but there we go. Now, you know, with a little bit of calibration, I'm able to pinpoint the camera to the bus, and it actually says it's a bus. And sometimes it's confused with a train because this thing actually looks like a train. That's not bad at all. So there we go. Now it's kind of stabilized. Perfect. So this is how, and now if you notice, the inferencing is pretty fast. You know, it is just a few milliseconds before it actually figures out what we're trying to detect. So that's the beauty of Intel Movidius. This is in action, where I'm able to perform live object classification. I'm actually working on a very interesting scenario. So I'm a big fan of pets. You know, I love dogs, and I have a dog, and I've been researching quite a bit about dog breeds and so on. So I already built a neural network model that detects the type of dog. You know, thankfully, some researchers from Stanford put up this huge data set of various dog breeds, and I basically used it to train a convolutional neural network. And as soon as I send the image of a dog, it basically detects and tells me what breed that dog is. Now, I'm already in the process of porting that to Intel Movidius, and my plan is to take this to one of the dog parks near my house and just point it to a dog and click a button, and I get an SMS about which breed the dog is. It's going to be pretty cool because I'm very curious and I'm fascinated about the number of breeds that are available and their traits, their personalities. So every time I see a dog, I think of the breed. And with neural networks and Intel Movidius, I want to move around with this camera, and I'm going to attach a tiny button to it. The moment I press the button, and it basically glows a bulb when it detects the dog. And the moment the bulb is glowing, it's an indicator that the dog is detected. And then I press a button and I get an SMS or a WhatsApp message using Twilio, which tells me what breed based on my neural network. It's a pretty cool way of moving around with a live camera and then detecting the dog breeds around you. So, that's another use case that I'm working on. I'm going to publish that as a detailed guide. So coming back, I want to summarize what we have discussed so far. So train the model at your favorite GPU cluster cloud. Could be Amazon, could be Microsoft Azure, could be Google Cloud ML Engine, doesn't matter. You bring it over to an Ubuntu box, you run MVCC compile, generate a graph, and you take the graph, move it over to Raspberry Pi and install NC SDK API, load the graph, perform some operations, and boom, you have a very low latency, high throughput inference even on a Raspberry Pi. So that's exactly what we have done in the previous two demos. Perfect. So that brings us almost to the end of this session. So we have discussed the overview of Intel Movidius, and remember, this is all about Intel Movidius NCS1. For NCS2, stay tuned. I'm going to cover OpenVINO Toolkit in depth. So I want to thank our sponsors, the New Stack, my media partner. And if you are fascinated by this demo and you want to learn more about it, watch out for a tutorial that's coming up tomorrow. That is going to be 15th of March at the New Stack. 15th or 16th, that tutorial should be up and running. And if you're watching this on YouTube, just click on the more link below and you will have a link to the article published at the New Stack. Foghorn is a Bay Area based edge computing company doing some pretty powerful analytics at the edge. Portworx, a container native storage company, again from Bay Area. They are our sponsors, and I want to thank these brands and these partners for supporting us. And I'm pretty excited about announcing the next session, which is going to be modern infrastructure, and it's all about Istio. I'm going to show you how to perform blue-green deployments with Istio. Even if you're not familiar with blue-green deployments, or if you're not familiar with Istio, don't bother. Just sign up for this session and I'm going to give you enough context to perform blue-green deployments with a very quick overview of Istio, and it's going to be a pretty cool, interesting live demo. So stay tuned for this and do sign up at mi2.live. This is going to be on March 28th at 9 a.m. PST and 9:30 p.m. India time. So it's time for Q&A, but before that, I want to bring up a poll, which I normally do for every webinar. So how relevant was the content? Excellent. Thanks for taking time and participating in this. I have one final poll. So how do you rate the overall quality of the webinar? This includes content, the audio, video, the quality of demos, the depth. Excellent. Thank you. Really appreciate it. All right. So let me see if there are any questions before we wrap up this session. So the question is there a standalone mode in the tools for products not on USB 3? Unfortunately not, but guess what? If you're really interested in using this with non-USB devices, you can directly build on top of Intel Myriad. So Myriad is the VPU, the Vision Processing Unit powering Movidius. Movidius just makes it easy to carry, easy form factor, and a plug and play like device. But if you really want to build something, you can always go for the Myriad chip. And if you are specifically interested in vision computing, I also recommend you to take a look at what is called Horn Sanjam. It is again powered by Intel Myriad, and it is a smart camera. It comes with its own SDK. It's a pretty tiny camera connected to an accelerator, and the accelerator connects to your machine, and they give you a very high level API and an SDK that you can use. So you can actually use Horn Sanjam, or you could use Myriad directly if you don't want to use a USB form factor. So I hope that clarifies this question. So thanks again for attending this webinar series, and I'll see you in the next session on March 28th at 9 a.m. PT and 9:30 p.m. IST. Thank you. And if you're watching this on YouTube, please do not forget to subscribe for my channel. I'm going to publish these videos very often. Thanks again.